And I should point out at this part that this point that I'm not doing this correctly. It should be an unsigned character I'm sticking in here. So these should be like a hex number, the hex ASCII representation of Z. But just to keep it, stay using hex numbers. I'll just keep going like this, improperly. But I guess maybe it's a little bit clearer this way. All right, so we got the Z put in. So let's put in another. I'll put T in next. Alright, so once again, it calls the queue is queue full. At this point, the size is 3. 3 is not equivalent to 8, so the buffer is not full. And it proceeds to the next line, where our tail is now resides at the third indexer. And then so we put a T goes in here, a little small t, lowercase t. Make this smaller. Alright. Okay, that's a T there, hard to read I know. And then post increment the tail. So the tail moves up to the next indexer. And modulus check. 4 divided by 8 leaves a remainder, and so the tail stays at 4, and the size is incremented, so I'll go from 3 to 4. Alright, next one. Let's put a 6 in there. To the full function, our size is 4. 4 is not equivalent to 8. Buffer's not full. Our tail is pointing at the 4 indexer. So we'll put a 6 replaces the 0 that's in there. And 6 divided by 8 leaves a remainder. Tail stays at 6. Size increments from 4 to 5. Go away. Just bear with me, we're going through a lot just to make a point, but I want to show when we get to the end that modulus, what basically what it's there for. Okay, our size is at 5. Let's check that 1, 2, 3, 4, 5. Alright, so we've in-queued 5 hex values. A, 2, Z, lowercase t, 6. See our tail is at the 4th, it's set to 4, the 4 indexer. And remember, your head always points to your oldest unread data. So obviously we haven't read anything yet, so our head is still stuck where it began, initialized at 0. And we'll get to that as soon as we finish here. So let's stick in lowercase u. and so calls calls the full function, and our size is 5. 5 is not equivalent to 8. The buffer is not full. Our data tail is pointing here. And I forgot to increment my tail. Tail should be here. Alright, so U replaces this 0. And our tail increments. Now we have 6 divided by 8 as a remainder, and so the tail stays at 6, and then our size increments by 1. Alright, finally, stick an R in there. Well, actually, almost there. Alright, is the buffer full? Size is 7. 7 is not equivalent to 8. Buffer's not full. It's almost full. Our data, our tail is pointing at the 6 indexer. So that's where our R is going to go, lowercase r. Post increment the tail. And our modulus is a 6. 6 divided by our modulus, so 7. Tail 7 divided by 8, still a remainder. So the tail stays at 7. And I think I have my size wrong. I must have incremented it incorrectly. Because it should be at 7 now. Oh, so I made a mistake back there in that last one. So I'll leave it at 7. I won't increment it because I already did. And our final, I'll put the number 4 in there. Alright, so calls the full function. And our size is 7. 7 is not equivalent to 8, so the buffer is not full, not yet, almost. So proceed to the next one. Our tail is pointing at the indexer 7, and so a 4 is going to go in here. Alright, now our tail is incremented. Our tail is now equal to 8. Now we get 8 divided by the Q size of 8. This leaves a 0. Leaves a 0 remainder. So the tail now becomes 0 and resets itself to the beginning. size increments 7, 8. Now, next thing we try, we still haven't read any of our data out. And this is what happens if you're not reading your data out fast enough as the data comes in. Because look in the next one, say we just receive another byte and we still haven't DQ'd anything. We still haven't read any data out of our buffer. So the next byte that comes in, say, is an E, or the hex number for ASCII number for E. Alright, so first thing it does, check if the buffer is full. So the size, which is now 8, is equivalent to the Q size, which is 8. So the buffer is full. So this will not continue on to the next line because the buffer is full at this point. So this is like a protection, because if this line wasn't in here, then at this point we're going to write this next value E, and it's going to overwrite the A that's already there. Just think about it. So the tail is set to 0 at this point, so it's just going to replace what D is assigned to, in this case E. It's going to replace that A with the letter E. So we just lost that initial data here, and we basically had a buffer overrun. We've gone to the end, come back to the beginning. If we didn't have this statement in here to protect us, now we'd start overwriting our data in our buffer, and we would lose any data that's overwritten. So that's why we need to DQ, at least keep up the rate of the DQ, so that to what's coming in, so we don't lose data if it's that critical. So then at this point, let's try reading something from our buffer using the DQ or the QDQ, calling the QDQ function. So we would use the same parameter QT as the pointer to our remember our pointer to our structure. And in the case of a DQ, and that's all we call. And then we assign a temporary, create a temporary variable here, myT, an unsigned character, initialized to 0 here. And then of course we check to see if our buffer is empty, our array is empty, because we don't want to read anything from it if it's empty, if there's no data has been put into it. Obviously we've put a whole bunch into it. But if we hadn't put any in, that's what that's for. So goes up and then checks, the empty function checks if the size is equivalent to 0. Obviously our size is not equivalent to 0, so the buffer is definitely not empty. Okay, so it proceeds to the next line. So now it's going to assign the temporary variable here, myT, unsigned character variable, and set it equal to the where the head is. So obviously the head points to the oldest data, and the head hasn't moved the whole time. It's been stuck down here. So it's basically going to pull. It's going to pull assign to myT the hex number, or the letter A, to myT here.